Hello friends, welcome back to my channel MEO exam. So friends, in this video we will study about few basic heat treatment processes which are very important and are mostly asked in exams. So let's begin with this video. So before we know the processes, we should know why heat treatment is actually carried out. So this is carried out to increase the hardness of the metal. Okay, so one is increasing the hardness, then again other is relieving the internal stresses, then improving the machinability, then improving the mechanical properties like tensile strength, ductility and shock resistance, then changing the grain size. Actually this is done for these properties, to enhance these properties, then increasing the resistance to corrosion by adding alloying elements, then to modify electrical and mechanical properties, then to change the chemical composition of metal surface, that is this is done for the surface hardening and surface heat treatment, and then to remove the trapped gases. So friends, this is the reason why heat treatment is carried out on workpiece. So heat treatment is basically defined as combined operation of heating and cooling of the metal or alloy in solid state for the purpose of obtaining desired changes in the properties. So this is the definition of heat treatment, that is heating and cooling of metal alloy in solid state for the purpose of obtaining desired changes in the property. Heat treatment includes heating the metal to predetermined temperature. Okay, that is the first step. Then holding the metal at that temperature until the structure becomes uniform throughout the mass, that is isothermal cooling, or basically holding at that particular temperature, or isothermal transformation I will say. Then cooling at predetermined rate to cause formation of desired change. Okay, then after holding we have to cool it at desired rate. Actually this cooling rate is determined by the medium in which it is cooled, like water, air, or under furnace, anything. So in this video friends, we will study about annealing, normalizing, and in next video we will study about hardening, tempering, or stamping, mar tempering, and this is case hardening is actually for the surface, and all other till 6, all these points as you can see over here, this is for the bulk. Okay friends, and this is for the surface. This is actually not that important because it is not, I have never heard surveyors asking all these things. So I'll tell you in detail about annealing, normalizing in this video, and in the next video about hardening, and then tempering, then os tempering and mar tempering, and case hardening is I will cover in next video. So let's begin with this video. So as we know that heat treatment is actually heating to a particular temperature, so that temperature we actually get from the phase diagram, and the cooling rate determines the microstructure, final microstructure which will be formed. So as we know that this phase diagrams, they only cover the composition and the temperature. Okay friends, they does not have anything to do with time. So for that there will be, then we will be using TTT curves or CCT curves. So the critical holding temperature for different heat treatments, we can see that this is the A1 line for the eutectoid temperatures. As we know, as I have told you friends, so this line, before this line is called eutectoid steels. Okay, then after this line till composition of carbon 2.0, means that from 0.76 percentage to 2 percentage, it is called hypereutectoid steels. Okay friends, so this line, as you can see, this line is called A3 line. Okay friends, and this line is called A1 line, and this line over here is called ACM line. These are the critical boundary lines that are that basically represents the temperature to which we are going to heat the specimen for the heat treatment. Okay friends, so A1 line is related to the eutectoid temperature. This is the eutectoid point, as we know. So this line is the eutectoid temperature line. Then A3 is the phase boundary between the austenite and two phase austenite plus ferrite. So this region is austenite plus ferrite and this is austenite. Okay, and ACM is the phase boundary between the austenite and two phase austenite plus cementite. So this region is austenite plus cementite and this is the austenite. Okay friends, now the microstructures, the microstructure formed will totally depend upon the rate at which the specimen is cooled. Okay friends, so cooling can be done in furnace, okay, in the air. It can be oil quenching can be done, and water quenching. So as we can see, this is the CCT curve or TTT curve. So this line you can see it is uh, called annealing and it is done in the furnace. Okay friends, then this is the curve for the normalizing, that is air cooled. Then this line, as you can, which you can see, this is the dotted line, is actually called critical cooling curve. Means that this is just touching the nose of this CCT curve or TTT curve. Okay friends, and the line, this line which you are seeing is because of water cooling or water quenching or oil quenching. So hope you have understood friends. This is for furnace cooling and the process is called annealing. Then we have air cooling, the process is called normalizing. Then this line is for hardening. Okay friends, so in this the perlite structure or perlite structure will not be formed, directly martensite structure will form, and for that we have to miss this nose of the curve. So now we will begin with the processes. So first process is annealing. So why this process actually done? So the purpose of annealing is to soften the steel and improve the machinability, then to relieve the internal stresses introduced by various previous treatments like rolling, forging, or uneven cooling. Then we can remove the coarse grains, or we can refine the grains. Then we can refine the grain size and the structure to improve the strength and the ductility, then alter the electrical and the magnetic properties. So this is what for annealing is carried out. So as you can see friends, this curve, this is the region that is representing the temperature for the annealing in this phase diagram, iron carbide phase diagram. So temperature is about temperature for annealing we have to heat at about 50 degrees Celsius above A3 temperature for hypoeutectoid steel. So friends, this is a hypoeutectoid steel, and for this is the A3 temperature line. So we have to heat above this line. Okay, so if this steel specimen is lying is hypoeutectoid, then for that we have to heat till it reaches here. Okay sir, okay friends, and for hypereutectoid steel, this one we have to heat so that it is above 50 degrees A1 temperature, that is this temperature. This is the A1 temperature, so we have to heat so that it lies in between here. We are not crossing ACM temperature to in this annealing. This we are not crossing this curve ACM temperature for annealing, and the reason is that uh, this continuous network of proeutectoid cementites in the austenite grains will be formed. As you remember, if you have not seen my video, then it will be very difficult friends. So for that you first go and watch my previous videos, because for this you have to understand that the microstructure for the hypereutectoid steels which is present over here is having boundaries with, if this is the boundary, then this is the pro-eutectoid cementite. Okay friends, so because of this, to avoid continuous formation of these pro-eutectoid cementite in the grain boundaries, we are not heating it to this ACM temperature, because this is very hard and this can lead to formation of crack or nucleation of crack, and the specimen or the material will fail without any warning. So for that purpose, in annealing we are just heating it to a temperature above eutectoid temperature for hyper eutectoid steels. Okay friends, and for hyper eutectoid steels we are heating above A3 temperature. Okay friend, so this is what for annealing we have to heat. Then there comes cooling. After heating we have to cool. So for cooling, it is done in the furnace, as I have already told you, to get the expected microstructure and the properties. For this we will get the porous microstructure, porous perlite structure we will get by doing very slow cooling rate. And in this the properties which the material will acquire will be low strength and it will have high ductility. So this is what the final workpiece will have. It will have low strength but high ductile. It will be highly ductile. Then the other process is called the normalizing. So this process provides the homogeneous structure consisting of ferrite and perlite for the hypoeutectoid steels, and perlite and cementite for the hypereutectoid steels. So this is what this is what the normalizing is all about. So purpose of doing is to produce harder and stronger steel than annealing. So as we have seen in the previous slides, that in annealing the strength is lost but ductility is increased. So to acquire the strength we do normalizing, that is we are basically increasing the rate of cooling. So to refine the grain structure of the steel to improve the machinability and tensile strength, then to modify and refine the grain structure, and then to obtain relatively good ductility without reducing the hardness and the strength. So basically the drawback of annealing was that the strength was reduced. So what this normalizing will do, this will uh, provide good ductility without reducing much strength or hardness. Okay friends, so that is why annealing is carried out. Now again the heating temperature. So for normalizing, the heating temperature is represented by this area or these lines. Okay friends, that is for hypoeutectoid steel we are crossing A3. Okay, okay friends, we are heating the specimen above 50 degrees above A3, and for the hypereutectoid temperature we are heating above ACM 50 degrees above ACM, about 50 degrees above ACM for the hypereutectoid steels. So you must be curious that for the annealing we are doing heating till over here, and for this we are heating above ACM. Then why in annealing we are not going above ACM? And the reason for that is that in this the rate of cooling is more as compared to annealing, because in this the cooling is carried out in air. Okay friends, so that does not lead to formation of continuous film of grain boundaries. Okay friends, as I have told you that in the structure the grain boundaries, if this is the grain boundaries, then the nucleation, this will not be continuous. Okay friends, as this kind of structure will be formed in this case, whereas in the annealing the grain boundaries were continuous. The pro-eutectoid cementite which was forming it, this was continuous. Okay friends, but in normalizing it will not be continuous, it will be nucleating and it will not be touching. These two are not joining. Okay friends, that is why we are taking it above ACM temperature. So hope friends this point is very clear. Then cooling is done in air, I have already told you. Then the properties which we will get in normalizing is fine microstructure compared to annealing, annealed workpiece, because we are doing faster cooling over here, and more strength because of that. Over here the ductility will be reduced as compared to annealing. Okay friends, for the this hyperretractoid steels. In the previous over here friends, you can see this is the annealing. So this is the cooling curve for the normalizing, sorry, this is the normalizing air cooling, and this is the curve representing the cooling curve. This is the start point for the transformation, and this is the stop point for the transformation. Now friends, as we know that the structure which is formed is having the cementite, pro-cementite in the grain boundaries, and the leftover structure which is formed is having laminar structure of cementite and ferrite. Okay friends, so this dark portion is the cementite. Okay friends, and this dark portion is the cementite, and this white portion is alpha or alpha ferrite. After this crosses the um, this eutectoid uh, temperature line. Okay friends, so in this region, if you say, you will have this kind of structure. So friends, these cementites are present in laminar structure, and so this kind of structure is actually not good for day-to-day application purpose, because this can lead to cracks. So for that, what we will do, we will convert these lamellas into spheroidal shapes. So that is why spheroidizing annealing is carried out. Spheroidization annealing is carried out. So when we are having cementite in perlite in an elongated laminar form, this is not a very good microstructure. So for that to take care of, we convert them into spherical cementites by the process spheroidization annealing. So let's see what this process is all about. So over here, as you can see friends, this area is represented by the spheroidization annealing, that is this eutectoid temperature. So basically the specimen or the workpiece is heated below A1 temperature to transform lamella cementite to globular cementites. Okay friends, so if this is the structure and these are the cementites, so these lamella cementites, they will get converted into sphericals or globules. So that is what happens in spheroidization annealing. So cooling rate is not specified, as no phase transformation is taking place. We are not crossing austenite boundaries, because we are just dealing with this, that is over here phase transformation is not taking place. That is why cooling rate is not specified for this. But if the product is big and cannot have fast cooling, otherwise should not have fast cooling, otherwise there will be thermal stresses in the material. So cooling basically depend upon the size of the product. So the properties which takes place or which changes in spheroidization is the ferrite matrix microstructure is formed due to reduction in interfacial energy, that is spherical shape is having minimum surface energy, surface area. So that is why these lamellar structure is getting converted into spherical shapes. This actually increases both strength and ductility. So this is what is done to convert this lamellar structure of cementites into globules. Then we have stress relief annealing. Then in this, the plastic deformation due to cold working, rolling operation or extrusion operation, welding process, etc. This process actually induces stresses in the material, and in some cases these stresses are not good for service applications. Okay friends, so to relieve these stresses, we have to carry out this stress relief annealing. So you can see in this area is represented by the stress relief annealing process. That is, this is the temperature range. As you can see in this, the product or the specimen is heated below or around 550 degrees Celsius. Okay friends, then cooling is carried out. This area I'm talking about. Then cooling is again it's not specified because the transformation is the phase transformation is not taking place over here, and the properties or the changes in the microstructure will be, there will be not much change, specific change in the microstructure, but stresses will be relieved and the properties will be restored as observed before particular operation. So the material or the product will have the properties similar to that which were before the product was formed. Then next is the recrystallization annealing or process annealing, I will say. They both are actually same. So after cold working to restore the strain hardening capacity. So friends, this thing I will try to explain when we will be studying about the stress strain curve. Okay friends. So this is something which we have to this is something has to do with this curve. So over here just keep this thing in mind, and this I will explain in when we will study about this curve. So after cold work to restore the strain hardening capacity of the material and to get the grain microstructure, this recrystallization treatment is given. So for this we have to heat to around 625 to 675 degrees Celsius. Then we have to, then cooling rate is again not specified, but it will depend upon the size of the product, and the properties will be find recrystallized microstructure will be formed, and this will have good strength ductility because the grain refinement of the microstructure. Okay friends, so this is the region where the recrystallization annealing will be taking place. So thank you friends, hope you have learned something from this video. In the next video I will study about we will study about hardening and tempering process. So till then, take care, have fun.